Okay, welcome to screencast, hopefully one and only, but we'll see, for Module 9, Lesson 1, and this is solving linear systems by graphing. So some of the stuff that I'm about to talk you through, you might have heard in the little preview set of notes, but this carries us into the first part of Module 9, Lesson 1, so we're just going to go through everything. So first of all, a system of linear equations, which is also known as a linear system, consists of two or more linear equations that have the same variables. Typically, for what we're going to do as, Algebra 1 students, I don't think we're going to run into any linear systems with more than two linear equations, but I mean, you could have a linear system with more than two equations. A solution of a system of linear equations with two variables is any ordered pair that satisfies all of the equations in that system. Okay, so let's get right to it. So let's look at A, and it says describe the relationship between the two lines in the following graph of a system of two equations. Okay, so we have this one that I kind of highlighted with a yellow, this one that I highlighted with a pink. The solution is where they intersect, okay? That's the solution of this linear system. They only intersect in one place, so there is only one solution to this linear system. Meaning that if I had the equation of both of these lines, there would only be one ordered pair that would make both of those equations true at the same time, okay? So, and it would be this ordered pair, whatever that is, okay? All right, B says, what do you know about every point on the graph of a linear equation? Linear equation, remember, like we're talking about one line, okay? A linear equation, one line, every point on that line is a solution to that linear. So just remember to keep everything straight. This is a system of linear equations because it's more than one line. Down here, they've kind of hopped back and they're just asking you about one specific A linear equation, okay? And every point on the line of a particular linear equation is a solution to that linear equation, okay? If you're talking about one line. All right, C, how many solutions does a system of two equations have if the graphs of the two equations intersect at exactly one point? Well, basically they're asking how many solutions do you have if this is the sort of situation you have where you've got two lines and they intersect at one point? Well, that means you have only one solution, and that is where the two lines intersect. Okay, so let's move down to D. Describe the relationship when the two lines coincide, as in the following graph of a system of two equations. Now, it's very hard to see because it basically looks like one line. But what if you had line that was red and then line that was green that sits right on top of the red line? Basically, you've got two lines that have the same equation. Well, the two lines are basically the same, so you've got a whole bunch of ordered pairs that would satisfy both lines, because remember, spoiler alert, they're really the same line, okay? So that would be an infinite number of solutions. Let me see if I can think of two lines in disguise that are really the same line. All right. Okay. So they look a little bit different, but if you had these two equations, they're really the same line. So you'd have an infinite number of solutions, for instance. So again, how many solutions does a system of two equations have if the graphs of the two equations intersect at infinitely many points? Meaning that the lines basically sit on top of each other. You would have an infinite number of solutions because the two lines are basically the same lines. Okay, F. Describe the relationship between the two lines in the following graph of a system of two equations. Well, here's your first line, here's your second line, and you don't have any symbolage or whatever, but basically those two lines are parallel, okay? And if lines are parallel, they're never going to cross. Parallel lines do not cross. So, how many solutions does a system of two equations like this have if the graphs of the two equations do not intersect? Well, if they never intersect, then there's no solution. Okay? There is no ordered pair that will satisfy both equations. Okay? All right, hop down to the bottom where it says explain number 1, solving consistent independent linear systems by graphing. All right. A consistent system is a system with at least one solution to it. Consistent systems can be either independent or dependent. An independent system has exactly one solution and one solution only. The graph of an independent system consists of two lines that intersect at exactly one point. A dependent system has infinitely many solutions. The graph of a dependent system consists of two coincident lines, in other words, the same line in disguise. A system that has no solution is an inconsistent system. Okay, so here's what I did. I took this information and kind of made a graphic organizer. So your systems of linear equations can either be consistent, meaning at least one solution, or inconsistent, meaning they have no solutions. If the system is consistent, then it's either an independent, consistent system, or it's a dependent, consistent system. Okay? Independent, one solution and only one solution. Dependent, you have an infinite number of solutions. Okay? All right. So the rest of Lesson 1 of Module 9 is going through and solving linear systems using the first method we're going to learn, which is graphing. Okay, so join me on page 405. All right, example 1 says to solve the system of linear equations by graphing. Here is your system of linear equations. Okay, personally, right now it's basically in standard form, which is fine. Because what they recommend that you do, and you don't have to do it this way, but what they recommend that you do is find your x and y intercept. Remember, you find your x-intercept by substituting 0 for y. You find your y-intercept by substituting 0 for x. So for this first equation, your x-intercept is 3, your y-intercept is 6, which gives you 2 points that you can graph. Over here, your x-intercept is -3, and your y-intercept is 3. Okay? I'm not real sure what they want you to do here, but the point is you have 3, 0 and 0, 6. That's 2 points. That's enough to graph this line. You have -3, 0 and 0, 3. That's enough to graph this line. So that's what they did down here. Okay. Like I said, I'm not real sure why they gave you a third point, although you could, just pick an x or a y and solve for the corresponding other variable. But anyway, take at least your x and y intercepts, graph the line. The solution to this system is where the lines cross. Okay, so it says graph the line, did that for you. Find the point of intersection, which is right there. And if you read the graph, that's 1, 4. So the two lines appear to intersect at 1, 4. Let's check to see if that is in fact the solution. I put 1 in for x and 4 in for y into both equations. So put 1 in for x, 4 in for y, 1 in for x, 4 in for y. And do I get a true statement for this? Yes, I do. Do I get a true statement over here? Yes, I do. So 1, 4 is a solution to this system because it makes both individual equations true. Okay? And ta-da, you have solved it by graphing. All right, let's look at the next one. find the intercepts for each equation, plus a third point for a check. I'm not going to worry too much about the third point, but if you want the x-intercept, remember, put 0 in for y. If you want the y-intercept, put 0 in for x. Okay, you've got your x and your y-intercept, x and y-intercept. I'm not going to worry too much about the third point. Although they generated here, if x is 3, then what's going to be y? If x is 1, what's going to be y, etc. Okay, plot the 2 points, and they appear to cross right there. That appears to be the intersection. Okay, it looks like that point is 2, 2. So verifying that 2, 2 is a solution, you put 2 in for x and 2 in for y into both equations, and make sure that 2, 2 satisfies both equations, or that 2, 2 makes both equations true. And it does, so that's our solution. In this case, and in this case, there is one and only one solution to the system. So if there is one and only one solution, that is an independent, consistent system. Okay? All right, join me on page 406.